This submarine Peter is holding right now isn't made for any normal lake or ocean. It's made specifically for frozen alpine lakes. It's packed with the newest advanced sensors and technology with the only purpose of swimming under the ice and measuring the ice thickness from underneath. So my question is, why on earth is a submarine needed for that? I thought you just need a drill like this, go through and measure with a tape or something. Maybe a submarine can do it without even drilling the ice? But if so, how does the sub even locate itself down there? We'll show you exactly how it's built, but if it's so high-tech, who tricked us into digging ice holes for 8 hours straight at 3,000 meters above sea level in the Swiss Alps?
And well, here's the story.
Well, to understand why this submarine is so important, we need to start from the very beginning and move to the other part of the Swiss Alps. St. Moritz. In 1907, the Swiss people of St. Moritz organized a new form of horse racing, ski joring. It took place on their frozen lake. They organized it every winter, and after 21 years it became so popular that they hosted Olympics with horse racing on ice. However, they also realized that there are risks involved. Relatively frequently, the horses fell and even died. For example, in 2017 in St. Moritz there was a crack in the ice, invisible from above, which turned the track into slush. The horses running at top speed fell into it, and unfortunately did not survive. You see, it's often not that simple to gauge the thickness of the ice on the lake. 100 years ago, basically the only option people had was to dig through the ice in multiple spots throughout the entire St. Moritz Lake. But it's not perfect. For that you'd need hundreds of measurements, which takes too much time to collect. So after 100 years of technology advancements, Swiss people are in search of a solution. As some of you know, me and Peter started building an autonomous submarine over a year ago and posted a YouTube video showing our build. After that, I received an email from an engineering student at ETH Zurich. They had an idea. What if we don't measure ice from above, but below, with a submarine similar to ours? I got really intrigued, of course, so we tried to help them on a call and follow their progress. Surprisingly, after just 5 months, they have already built what we're about to see today. Now, to investigate further and learn how exactly the submarine works, we will join them on their first real mission. The goal is to create an ice thickness map of a lake. We just need to travel about 1,300 kilometers to meet our new friends in Switzerland. So we got on a plane.
In all honesty, this is kind of hardcore to climb there.
We could finally meet the person behind it all.
How are you?
Hi, nice to meet you.
Nice to meet you. It's really early in the morning.
Yeah. This is Richard Rudin, one of the people responsible for this project, and also the student who wrote to us initially.
How many of you are there in the group?
10 of us that are working like full-time on the project.
Full time?
Yeah,
I mean,
full-time.
8 hours?
Yeah.
Oh wow,
Okay.
So it's
Alright.
taken over. Like.
I underestimated the amount of effort, I guess.
They called it Polaris. It's my first time in Switzerland.
What, you're going to Zermatt?
Yeah, immediately. They were about to start the mission, but to be honest, we still don't entirely know what makes the submarine better than other methods. So what's the issue with measuring ice?
Just as an example, in St. Moritz, where we have like hundreds of people on the ice, we have horse racing, we have car racing, all of that. We looked at a map of like ice thickness measurements, and they only had like 2 dozen.
Do you think drilling holes is like more time consuming?
It is very time consuming, and they usually have to send out firemen, like firefighters, out onto the lake to do it, because it's also unsafe if you don't know how thick the lake is. Like you can make a hole here and then see, okay, it's 30 centimeters, but then you walk further in and localized, it might be very different. We built our system for even when we have ice flows, you could still measure it. And if you have ice
What
flows,
is ice flows?
that's like the stuff, like an iceberg.
Okay, so why is that a problem to measure the ice thickness from the top?
You cannot.
How would you get there?
How would you get there?
Oh, how would I get there?
Yeah.
Okay.
We already verified that our ice thickness sensor, we verified it in the lake of St. Moritz, where the ice sheet was 50 centimeters thick, and it worked perfectly there.
Wow. Okay.
So that's great. But
Okay, so because I think that when we talked for the first time, you said something about a sonar or like an ultrasonic sensor or whatever.
This is the thing we don't understand yet. What kind of sensor is this and how does it measure ice thickness? In order to see for ourselves, we need to transport everything to a lake.
And it was like summer yesterday. Yep.
This is Theodul Gletschersee. We're right below Matterhorn, which is that famous super dangerous mountain. We needed to get to 3,000 meters above sea level because it's already late enough in the year and none of the lakes in the valleys are frozen. In order to get the submarine under the ice, we of course need to make a hole, but theoretically just one. It should take just a moment. But meanwhile, we were finally able to see the submarine itself. Nice. Wow, it's bigger than I expected. Right away, Richard started explaining the ice measuring sensors.
So this is just a weak transducer. Okay. This is our sonar. So the very strong transducer. Right.
So this is how the sonar works. It sends sound waves up into the ice. Then some of them bounce back immediately, but some go through and bounce from here, where the ice and air intersect. Now there are two sounds coming back to the microphone with a delay between them. And from the time difference, it's theoretically possible to calculate the ice thickness. The Polaris team had tested this method already and got some promising results, but here's the thing, they are not certain whether it will work during the real mission. We'll see that in a bit. Now the sonar can't work by itself, of course, it somehow needs to move underwater exactly how they need it to, so that's what they spend the majority of their work on.
This is our main computing unit. It's a
Jetson.
GX, yeah. Here's our batteries. They have like double the capacity of what we had before. Cool.
I like the strain relief. This is a very cool idea.
I'm stealing that. Yeah, it's really cool.
And you have a nice tray, you see? Is it cement?
It's cement. You can look at it from here, you can actually see it, it's cement.
Oh, nice. Okay. This solution is pretty clever because it's really easy to adjust the center of gravity. How many motors are there? 1, 2, 3, 4, 5, 6. Okay. And so 6 degrees of freedom.
Yeah.
6 motors make the sub very maneuverable. It can move in all axes, which is very useful in this case. What's this?
This is just to keep the weight balance, like the buoyancy balance right now.
Nice. It's a rock for balance.
Yeah,
we're using a rock.
Yeah, we use that's super high tech.
Nice. Yeah.
The rock is just a placeholder for this localization beacon, which has to do with an underwater antenna. We'll talk more about it later when the drone is in the water. Now the Polaris team had to set up all of their gear. They have a lot of gear.
Then
That's a fun computer. You know how much it costs?
Like 5,000, I think, yeah.
It's built into the box. Wow. This is their portable command center, from which they'll steer everything. Now we should be ready to put the sub into the hole, but something is not going as expected. Maxi, with the chainsaw, couldn't get all the way through, probably because his tool was too short. Now we didn't come all the way here to bail, so Peter and Richard got some more long, heavy tools from the station.
But you can actually see the second ice sheet and we've actually broken through. Okay, it's pretty good.
Have you made any ice holes before like this?
No, but I like this one.
It's challenging.
It's a very manly challenge.
Yeah. Typically on other lakes we wouldn't need to make a hole, but it was so cold here that we couldn't find any inlet. Do you think it's the other ice layer?
Yeah, I think so.
I've never heard of it, but it turns out there can be multiple ice layers on one lake. This makes us question whether the sonar will actually work. It's supposedly common in Alpine lakes, where the weather conditions are very variable. When the top of the lake is frozen and a thick layer of snow falls, the ice gets pushed down. When the temperature drops again, it freezes the upper snow, leaving slush in between. I think you can find it useful.
Yeah, this is my best work here.
After a whole lot of efforts and tries, it turned out that there was a third ice layer even deeper, which we couldn't get through no matter what.
So I'm not sure if we broke through it. No, honestly, I don't know.
But I think we might have figured out something else. You said there's another lake close by.
Yeah, very close by, one station down.
Okay, so we decided to move because the ice here is too thick, which is ironic. There aren't any other good lakes here, so this is our last hope. This is Schwarzsee. It's a couple hundred meters lower, so it should be slightly warmer and therefore easier to get through the ice. Yeah, it seems better.
Okay, watch out.
We just broke through the ice and I'm confident we can get through the second layer as well.
So we kept digging for another 3 hours. Peter had to rescue our tool. And by then we are almost ready with the hull. We just need to see how deep is it and check the conditions underneath the ice. This is our upgraded CPS3 and we'll see how the underneath the ice looks like with this.
Oh yeah, I see the bottom. That's how it looks like. Oh yeah, this is the bottom. There's a lot of like algae here and stuff. Let's see the top. Yeah, so this is the ice from the bottom.
You're quite far now.
Oh, there's a fish.
It seems like it's more or less the same height everywhere throughout,
Yeah.
because then we have no issues.
If you also happen to have an Alpine lake in your backyard, or any lake for that matter, you can build your own underwater drone and assemble CPS3 yourself, just like Jost did in February this year. He used components from our kit, and while doing so he even modified the remote with a 3D print. He shared that on our Discord. After a few adjustments in his bathtub, he made the drone neutrally buoyant and could go to a lake to find some hidden wildlife. Recently, he even attended a festival showcasing his build. So if you'd like to build an underwater drone yourself, for a limited time we are giving a completely free full instruction manual with design files, code and everything. So after watching this video, sign up and get all instructions with the link in the description. Again, it's free, and if you decide to build it, you can get a DIY kit from us with all the components you need already in the box. So the lake seems promising, but it was already quite late. We need to wake up early tomorrow if we want the entire mission to work out in just one day. It's 4:40 and we're awake because we need to get to the Matterhorn extremely early. So early morning we traveled back to our mission site. It's the next day
Next dollar.
and we are here. And it looks like the hole is still here. And the tent is here.
Plan for now is to put the sub in the water. We're just gonna drive around, make sure everything works at first.
Oh, this is your plan for the mission.
Yeah. In theory, we would do the 100 times 100 meter grid.
But starting with 10 by 10?
Yeah, like the goal first is like to just do a whole drive.
The plan is simple. After we make sure everything works, we'll make a 10 by 10 meter square mission with 4 ice thickness measurements. And if that works, a 30 by 30 meter mission with 16 waypoints. In order to check if the submarine can find itself accurately underwater, we can even make a second hull and check if the sub emerges after we attempted to swim in a straight line. First waypoint there. Thankfully, Maxi just bought a new, much longer chainsaw to do that.
Nice.
Great, it's time to submerge the drone in the Alpine lake. The drone weighs about 30 kilograms, so it's a bit heavier than anything we've ever built.
Okay.
Slightly positively buoyant, right?
It's supposed to be.
Yeah.
Okay, perfect.
Wow.
And now you synchronize the all the GPSs, I guess, all the location systems. Let's see how it looks like in the command center.
The location? You can see that here.
Oh, nice. Depth 18 centimeters. And you'll be steering the drone, or
I can.
with this?
Yeah.
Let's swim with the drone now.
Is this the correct direction?
Well, we have an issue. As you can see, the localization data from our two sources is completely opposite. That means we have to somehow synchronize it. It will be crucial for knowing where exactly we make our ice measurements. But what exactly happens? And since everything is underwater, how does it work exactly? After all, we can't see it. The Submarine has a very precise GPS RTK module, but as you probably know, GPS shouldn't work underwater. Well, Polaris have figured out that this big cylinder with air around the GPS can help a lot.
Well, the GPS with RTK, real-time kinematic, that's the most accurate positional fix you could get. So we put it in there, the GPS takes the first reference and we know exactly where the sub is, up to like 1.4 centimeters accuracy.
You can see here, GPS is at the moment 1.4 centimeter in horizontal accuracy.
That's super accurate then.
And so you put it on the very top, so that you said you can touch the ice, and then you found out that if you touch the ice, it can still work, even though it's underwater. Turns out that if you turn liquid water into solid water, ice, the GPS radio waves suddenly can travel much further and penetrate even a thick layer of ice. If we encase the GPS in a large air tank and then touch the ice from underneath, it's almost as if the GPS is on the surface. And there's a very large container, so that there's a lot of air around the GPS.
In nautical terms, it's called a radome. You can see those on ships and on airplanes. And what they do is they keep water away from the GPS antennas so they don't interfere with the signals.
But this solution has also its shortcomings.
I'm checking right now if I'm getting GPS at the ice. GPS worked. We had like not the best accuracy. It was an accuracy of 2.5 meter peak.
While swimming, we can't always reliably touch the ice from underneath. Therefore, we'll need something that works for all depths. That's why SBL exists. Stands for short baseline. Now, underwater navigation is generally extremely hard because, as you know, radio waves don't penetrate liquid water. Even your phone disconnects immediately when submerged. But thankfully, there's this thing called sound. Maybe you heard of it.
It depends on like in which angle these transducers like also receive this wave, and you can see like from which angle you now got it.
If you have 3 microphones and something gets very loud underwater, you can see which microphone got the audio signal first. You can also see how long did it take to reach the next microphone and then the third. And because we know the speed of sound, we can triangulate the location. My understanding was that you need to have these microphones pretty far apart.
There are 3 systems and they all work very similarly. One is long baseline, these can be kilometers apart. Then the SBL short baseline system where it's only like meters apart, if even. And then there's the ultra short baseline, USBL, which is really small. It's just basically one big transducer.
Turns out the microphones don't need to be that far apart, and that's where this antenna comes in. As you can see, there are 3 hydrophones on 3 of its ends. There's one beacon on the Submarine which emits these sound waves. And do you know the accuracy of this one?
Yeah, it's about 1 to 2 meters in our case.
SBL isn't perfect when it comes to accuracy, but combined with occasional GPS readings, it's overall very accurate. From our previous videos, you might remember that there's also a third way to get location, and that's through a DVL that sends sound waves into the lake bottom. But for now, Polaris focused on these other methods. We'll talk more about DVLs in the next video. Meanwhile, the second hole is almost ready. Okay, these ice blocks look very impressive.
Yeah.
You think it's big enough?
Yeah, it's big enough.
After some minor calibration issues and fixing it with a compass, let's see if the navigation works now. The 2-hole drive. The submarine needs to swim in relatively straight line to reveal itself in the second hole 10 meters apart. Then in reverse back to the first one. Let's go.
Oh, it seems to be in the same direction now.
This is why we have yellow prints and not black prints.
Yeah, that's useful. It's here.
Nice.
And coming back. It's to the right.
Nog een iets zu mir, gut, stopp, hinderen. Achtung, macht sie das Sache.
Seems successful, moderately successful. It went back almost to the same spot.
When you said like to the right, I saw on the map I was also shifted to the right.
The map was super accurate.
Look at that path. You can see like after the filtering, how much cleaner it is than like with the...
Yeah, it looks extremely smooth. With this, we are ready for the grid test with the ice thickness measurements. The thing we are all here for. It's a 10 by 10 meter square for now. Let's go for the square. The debug took a lot of time, and some of us were pretty tired at this point. Peter, I know you're tired, but they're going for the square now.
Dora,
You need to see this.
I need to see this?
Yes.
Right.
Now we go from the first hole to the second, and then turn right towards 2 more waypoints. Let's go.
Let's go.
The purple dots are the constant SBL readings, which allow us to precisely go to the waypoints.
Yeah, we can try to go further down.
I see it. It's here. Yes, yes. Yep.
And I'll do another right turn, so...
So it's somewhere here. We don't know where.
It's finally time to measure the ice here, but we have an issue. Even though the method using the sonar seemed promising earlier, now there's too much noise in the signal, and we can't really make out useful data. Some military researchers seem to be developing this technology, but it's extremely difficult to make it reliable. Therefore, here Polaris are using a slightly simpler method. Instead of looking at both reflections, we look at only the first ping. From the delay, we know the distance from the sub to the bottom of the ice sheet. If we could get a distance from the submarine to the top of the ice sheet, we could subtract the two and get its thickness. Thankfully, there exist those very simple sensors that can read hydrostatic pressure. From the pressure you get the depth, and since the density of the ice is slightly smaller than water, it always floats on top, so we can get the distance to the top. But now with a depth sensor we have an even simpler way to do it. Just ram into the ice and measure the depth, keeping in mind that we also have to subtract the height of the submarine. That's why Polaris is using both of these simpler methods, and at each waypoint they swim up and touch the ice. Where's the ice detection?
It's this bool value over there.
Oh,
Yeah.
true. Going to the 4th waypoint, so there.
And now we go another 90 degrees.
And now we're coming back. Almost there?
Yes.
That was the first real Polaris mission, and with that another day has passed. That's it. Me and Peter had to travel back, but meanwhile Polaris went back and on their last day here performed the bigger mission. After some post-processing they got this map. On the right here we can see the scale of how thick the ice is, which is represented by the gradient on the map. This one was created with only pressure sensor measurements, and this one done with the sonar has a bit more resolution. So, is an ice measuring submarine better than a traditional method? Well, on one hand it's pretty accurate, and once the sub is in the water they could survey the ice pretty quick. On the other hand, with the current sonar methods we can't measure the thickness of the top ice layer alone. It may be possible using the methods with multiple sonar reflections, but needs a lot of noise reduction. Also, ever since Polaris is working hard on making the drone autonomous. Here's one of the missions they've done since. Their next under ice mission will happen next winter, so keep your fingers crossed and subscribe.
Also, right now we're still working on making our CPS-3 drone even better. So right now we've released a couple of upgrades, like for example an underwater gripper that you've seen in this video, some stronger underwater lights, and we're working on many more.
Yes, so if you ever wanted to build one of our projects, I think this is the best way to do that. All the models, instructions and programs are for free, and if you like it you can get an assembly kit from us as well.
The link is in the description, so check it out.
See you in the next video!